Students, welcome to video class 8, and in this session we are going to deal with the block diagram representation of a system. Now we know that in a block diagram we have seen some in the previous videos how to frame up a block diagram from a given mathematical equations. Okay, just as we have seen in the very simplest example that we did, that's in a simple RC circuit, and we first of all we went on to derive various we went on to find out various equations, and using those proper equations and proper substitutions we have arrived at this block diagram. So I'll show you one more example which we did. So now, in comparison to the above circuit which I have shown right now, this is a bit more complex. Now what happens? The complexity increases as the components increases. There you have only considered an RC network. You have to have here you have two RC network connected together. So that means some amount of complexity is there. That also reflects in its block diagram, right? Now this is no longer a simple block diagram as we have seen here, right? Now looking carefully at this block diagram, coming to this, what is basically a block diagram? Now this is actually a simplest of the block diagram, with each blocks showing what? Showing the interrelationship between the input and the output. So now, keeping this in mind, imagine that you have a very a chemical plant, chemical factory which consists of a lot of plants and a lot of processes which are to be controlled. Say, for example, you have too much of boilers, steamers, and where pressure, temperature, and all these things are to be measured frequently and are to be controlled. So when you represent each components in that plant can be considered as a block, and you can evaluate the individual transfer function of each components, and you can develop a block diagram of a big complex, and that block diagram will also be complex, just as we seen in the second example right now. Okay, now the thing is that now that is actually a type of representing or type of representation of a input and a output system. So you'll be having a lot of blocks as we have seen right now, as we have seen in this example. So in this example, because of the presence of one more R2Z2, you have three blocks and three summers, and it becomes more complex. Now, even though these complexity is true, you know the basic block diagram of this, which we have studied in the first or the second class, I think. What is this? This is actually a simple block diagram of a closed loop control system. You have a summer, you have a forward path gain, and you have a feedback gain, and it is represented in time domain. R of S, C of S is the output, R of S is the input. You have a summer, you have a block, and a feedback gain, which is represented as H of S. Now this type of representation we call as the canonical form of a feedback system. This is called as a canonical form of a feedback system, and you have already derived the transfer function of this C of S by R of S is equal to GS by 1 plus GSHS. Now, what is the purpose of this block diagram representation? Now, all the block diagram representation is from this block diagram representation. Once if you know the block diagram representation, you don't have to go through these equations to find out the transfer function. You can very well find out the transfer function. Now, the question that comes into your mind is, how will you find out a complex how will you find out the transfer function, which is a complex block diagram just as shown here? Now the thing is that if by some means, you don't have to, for the meantime you don't have to worry about that means. For by some means, if you can convert this huge block diagram into this block diagram, you can find out what? You can find out the transfer function by using this equation. So this technique of bringing a complex diagram into a simple or a canonical form of feedback system is what is called as a block diagram reduction technique. Once if you can convert a very complex diagram into this, you can straight away use this expression to find out the transfer function. And at that time, you will say that this is much easier in comparison to the direct evaluation of the transfer function which we did previously. Okay, now just a recap of which thing which we have derived in the previous videos. That is, say, consider a simple RC network, and we have found out the transfer function to be 1 by 1 plus RCS mathematically, right? And I have also drawn the block diagram of that, as you have just seen that. Now, once this block diagram is represented, this is of the canonical form, right? Okay, this is of this form. So now that's the objective of reduction. So some way or other you should convert any block diagram. You can convert any block diagram in this form. Once if you found this is a transfer function. This is a block which represents a transfer function which relates the input and the output coming over here. Now using this is your GS and this is your HS, right? Okay, so GS is 1 by RCS, HS is equal to 1. Once if you get this, apply this equation to get the transfer function as. So just substituting GS and RS, HS here in this equation, you will arrive at 1 by 1 plus RCS. So hope you understood the technique behind this. So the objective is converting a complex block diagram into canonical form and use the equation for the canonical form to get the transfer function. Okay, now before going into the block diagram reduction technique, you should have some idea about block diagram terminologies. Now there are three important parts in a block diagram. Okay, so number one is the pick-off point, or it is also called as a take-off point. Second one is a block, and the third one is a summing point. I will just show you in this figure what are all these things. So you can say this one is a pick-off point, this one is a pick-off point, and this is the summing point. Okay, and this is a block, and this one also can be represented by a block. You can write this inside as one. So these are the two blocks in this block diagram. So what are the various components that you can find in a block diagram? Pick-off point, block, and summing point. Do I need to explain it? It's so self-explanatory, right? The pick-off point is also called as a take-off point. Now why it is called as a take-off point? All these points so this is also another take-off point. All the points. Now this is actually the point from where the signal is taken to the other part. So right now this is also a take-off point where the signal is taken to this part, right? So all this node that's coming at the block diagram is referred as the take-off node, or okay. So sometimes in some text you can say that this is the beginning node and then node. Anyway, this all comes under as take-off point or pick-off point. This can also be considered as a take-off point. Why? Because even though it's the end node, from this node also some signal is taken to this side. So the point from where you take the signal can be called as a pick-off point or the take-off point. And blocks, as I mentioned to you, that a big complex thing can be considered as can be represented in various small blocks, and each blocks represent the relationship between the input and the output. Here, look at this. So this is actually the input, say, coming at, they call it as small x, and this is y. The input x and y has a relationship that is called as 1 by RCS, and that is represented by the block. Now what is a summing point? Summing point is also called as a comparator, where you actually sum up the signal that is fed back, or it is not necessary that it has to be always the feedback signal. Any signal can be added or subtracted now using this summing point. So these are the three components that you can see. Say for example, I've shown you an example. Say you have a summer here. You have three signals, x1 of t, x2 of t, and x3 of t. Two are plus and other one is minus. So what's going to be the output signal? The output signal of the summer will be x1 of t plus x2 of t minus x3 of t. Okay. Now let's see some of the simple block diagram protection techniques, or some of the scenarios that we come across when we deal with complex block diagram. Say you can see in some block diagrams, you can see combination of two blocks like this, G1, G2. And this connection we call as the cascade connection, or this blocks. So this is a scenario where blocks are arranged, blocks are cascaded. So this is a cascade connection. So blocks in cascade. You can call this scenario as blocks in cascade. Now, how will you find out this transfer function of this? The simple transfer function of this will be, see, what is this transfer function? The overall input is x of s, and the overall output is z of s. Now let us see. Say for example, if this x of s is your input and g1 of s is your transfer function, then what will be your y of s? Y of s will be g1 of s. So your y of s will be g1 of s, or g1 into x of s, right? Now this is the input to the g2 of s. Now what happens to this input? This also gets multiplied with g2 to get z of s. Now what is this? Basically, what is this z of s? Z of s is equal to x of s into, what is this? This is actually g1, g2 of s. So that means you can reduce this into a single block, right? As g1, g2, what is this? Showing the overall input and the overall output at this. So what is the transfer function of this? This is z by x of s, which is equal to, say, z by. So from this you can find out the transfer function, that is equal to g1, g2, right? So in a particular block diagram, if you come across this scenario, you can simply replace that by a single block as g1 into g2, and that scenario we call as the block in cascade. Look at this. You have another scenario where you have g1 of s and g2 of s, and two parallel branches, they connected together. Now why this I'm calling this as parallel? Because both the ends, each blocks are having start from same end and ends at the same end. So this type of block arrangement we call as a blocks in parallel. So this can be another scenario you can come across while doing complex block diagram. Now how to represent that scenario? Say assume that you have an A. This A is common for these two branches. Just as voltage is same as in the parallel branches, so you can say consider this as A, this also as A. So that A means it is x of s, right? I'm just explaining it for the sake of explanation. So what will be this output? This output will be whatever is coming at this, that times g1 of s, right? So this will be g1 of s into A. This will be g2 of s into A, or g1 of s into x of s into g2 of s into x of s, right? Okay, now where A is actually your x of s. Now what happens at this? This is a summer. So what will be this? The summing action will take place like this: g1 of s plus it's like this, g1 of s into A plus g2 of s into A, right? So you can take the A outside. So this will be g1 of s plus g2 of s into A. And what is this A? A is x of s, right? So what is this? This can be replaced by a single block diagram as g1 of s plus g2 of s. Okay, so this is called as a blocks in parallel. Now look at this, and another scenario that can come across is this one. So you have a summer, you have a summing point here and a block. Suppose if you want to convert, if you want to take away this summer point to the right side of this GFS, so why do we need to do that? At times, what is our main objective? Our main objective is to convert any block diagram into the canonical form, or into that simplest form. So during our observations, we will feel that if this summer would have been in this position, then I could have converted this, then I converted into its canonical form. If such thought comes, there must be provision to transform this signal from the summing point to the other side. Now what must be the thing that you need to consider in mind is, wherever the position is interchanged, the signal that comes out here must be the same even after interchanging. Okay, that's the key of this. That is should be remembered. You cannot just change the position as you wish. You need to change. You need to do some necessary changes so that the output always remains. Output is unaffected due to the change. Okay, that's the thread of this. Now look at the summer. You have a summer, and I can change the position of this summer even after GS. The only thing is that I need to make a special arrangement along with this Z of S. You need to, after Z of S, this Z of S has to pass through a block J of S. I will explain how it is. See, look at this. What is the signal that comes over here? This is X of S minus Z of S. Now what will happen when it comes over here? This will be X of S into G of S minus Z of S into G of S. Okay. Now what I want to get is, what I want to get is, I want to get the same output here even after if I change the summing point. Now let us see, will I be getting that? Okay. Now what happens when this change to this position? This Z of S, see, look at this. See, if suppose you are not adding this, you are just adding Z of S, what you are going to get the output is, see, what is the output here? It will be X of S into G of S, and this will be X of S into G of S minus Z of S, right? That's going to be, if this would if there is no block here, then it would have been minus Z of S, which is not the output that is shown in the first figure. So if it needs to be Z of S into G of S, this Z of S has to be separately multiplied by another G of S. Okay, so now let us see. So this will be ZS into G of S, right? Z of S into G of S, you are getting the same expression. So this is how you should go through it, find out the necessary changes. And you cannot be by heart, you don't need to by heart all these things, because it's not possible. So do as many problems, and then you will come across different scenarios, logically change the necessary, do the necessary changes, so that keep in mind, whatever change you do, whether to change the summing point from one point to the other, the output has to remain the same. So this is actually a scenario. Let us name the scenario. This is moving a summing junction or a summing point to right past a block. Okay, moving a summing point to the right past a block, that means to the right side of this block. Okay, the thing is that you need to do this sign, okay, this change. Hope you understood this. Okay, coming to the next scenario, where you have say this one, you have a block before the summer. Now when you have observed, you have seen that it would have been nice if this block diagram reaches the right. Suppose, imagine that scenario, that is something like this. So what change should I do? So I will again, for the simplicity, I'm just using A. A is actually your X of S, right? Now what is this signal? This is actually A into G of S. So let us call this as B. And this is actually Z of S. I'm just calling it as B. So this is going to be A GS minus B, right? Now I want to get the same signal, right? I'm calling X of S as A, Z of S as B. Now if there would have been no signal, what will be the output here? This will be A minus B. It is straight away. If suppose B is straight away fed, it will be A minus B. And what is going to be this? A into GS minus B into GS. What is the signal that you require? You require A into GS minus B. You don't, this is unwanted here, right? So how will you take away this GS? Suppose if you can add a block as 1 by GS, this will be multiplied by B into 1 by GS. So the signal will be B into 1 by Gs, 1 by Gs. And when this passes through this G of S, this will get cancelled, giving you A into G of S minus B, right? Okay, so that's the signal that you want. So this is the way. Okay, so you need to do appropriate changes in each branch. Keep this in mind, the output should not be altered even if you change. Now what is the objective of changing? The objective of changing is to convert a block diagram, a complex block, into its canonical form. Okay, so what you will call for this scenario, so you can call this as moving a, you are actually moving a block, right? Moving a summing junction, moving a summing junction. Okay, that's what happened. So this summer is moved to this position after the, before the block, that is moving a summing junction to left past a block, left past a block. Okay, now you have two more simple scenarios. Say here you have a, what is this called? This point is called as a takeoff point, right? TOP, takeoff point. Now this takeoff point I need to change to this position after the block, right? Now what changes has to be, this is without any G of S. Once it comes to this position, this signal will be having a GS. So in order to compensate that, you need to put a block diagram with 1 by GS, so that you will get the same X of S here. Okay, so the takeoff point, even if the takeoff point changes, you should get this X of S in order to get this. So now once this signal passes through this, you will have X of S into G of S, but this has to be X of S. So in order to have this output, you need to take this X of S while multiply by 1 by GS, so that you will get X of S. So what is this scenario? Moving a, this is actually moving a pick-off point right past a block, right past a block. This is much simpler in comparison to the other. Now what must be this? This is actually the reverse of that, moving a pick-off point left past a block, left past a block. So here it is. So you want to change this takeoff point to this side. So what happens? This is actually X of S. So what is your Y of S? Y of S is X of S into G of S, right? Now once if you move without this addition, what happens? The signal is going to be X of S. You need to multiply this by a G of S. So you need to add a block like this, GS. Then this particular signal multiplies by H of S, so that you can, you must understand that this can be a part of a block. So I'm just showing only this one. So you can change this point, this pick-off point, to the other point without altering any of the output of the system. Okay, so these are the different scenarios that you can come across. So as I told you, though, it is not to be by hearted, but rather try to do this with logic and do appropriate changes. So our main objective is to convert it into a canonical form. I'll just explain what we have learned here. Say suppose this is a pick-off point right part of a block. Look at this expression which we have, this block diagram which we have already seen. See, look at this. Now can you just, I'm considering only this part. Can you call this as a canonical form? No, you cannot call this as a, why? The reason is this. This is the objection, right? This one, this point. If there would have been no point like this, right? Then you will call this as the canonical form. Why canonical form? You have a G of S, you have an H of S. So this is your canonical form. This cannot be called as a canonical form because another takeoff point is there in between this. So this is not a canonical form. So what if I can change this to this side? That is that you are changing the takeoff point right past this block. Okay. Now when you do this right past, what is this signal? The signal should not have any effect of 1 by C2S. Right? Right? Okay, now if this needs to come over this, what you need to change, you need to do a change here. So this is a scenario. You have a 1 by C2s, and call this is your I2 of s, right? Now this I2 of s node has to be brought here. That's the situation. But this is a equal to 1. This is a unity feedback. Now still, even if this I2 of s comes over here, or this node comes over here, still it should be unity feedback. That means the output should be I2 of s. Now what happens at this side? When it comes to this side, it will be I2 of s into C2 into 1 by C2s. So in order to get I2s, multiply this by C2s. You need to add a extra block on this RF line so that you can bring this together, right? Now once if you bring this, now considering this one you can consider this as a canonical form. So what you can do, you can reduce this whole canonical form into a single block. What? By using that expression gs by 1 plus gs hs. Okay, right? Now once you brought this, you can convert that this one. Imagine that it has been brought over here, so this block can be considered as, okay, as a single block. You can replace that block by using gs by 1 plus gs hs. Okay, right? So you will understand when we do that problem. I'm just giving you an example only. Okay.